Hey, morning, everyone. Okay, I think we can start the lecture now. Okay, it's 10:32. Okay, so this week we will continue about the matching problem. Okay, so I mean, yeah, last lecture, this Tuesday, right? We are already learning about how the bipartite matching and what is the network flows. Now we continue with that. So we know that, okay, for the, let me, okay. So we know that the matching problem and the network flow, they have the connection. For example, if you have the matching problem, for example, from A, B, C, D, E, F, you match with 1, 2, 3, 4, 5, 6. So actually you can convert it into the network flow problem by just introducing the source and the sink node. And then you connect the source to on the left-hand side and the sink to the right-hand side. And the maximums and the matching problem will be converted into the network flow problem. For example, find the maximum size of the bipartite matching will be equal to the solving the network flow, so that later we just see what is the maximum flow that can flow into the sink. Okay, so it's exactly the same, right? Because if it can match from for example, the left-hand side to the right-hand side, they will flow into the sink, right? So area not flow in the sink. So we just count the total here. Then we can get the maximum number, okay? And because we convert the bipartite matching into the network flow, so the capacity, okay, the capacity of the flow and also the flow is on 1. It means that if there's a connection, then the capacity is 1. Okay, and later if there's the flow side also 1, right? So it's just a simplified problem of the network flow. Network flow, the capacity and the size can be more than 1, but now everything is just restricted to 1. Okay. So so this Tuesday we also learn about the 4 Ferguson methods, right? 4 Ferguson methods. It's about we just finding additional flow in the network using the residual network. Okay, and the flow in the residual network we will calculate by just the capacity of the original network minus the flow we found. Okay. Then at the beginning, because there's no flow, so the residual network will be equal to the original network, so they are identical. So why the original network? Then this is also the residual network. For example, this is the original network. Then we can say that it is also the residual network at the beginning. Okay. Then for the fork Ferguson methods, they do the finding the additional flow, right? So for each iteration, okay, so for each iteration, we just find an armating path from P, from the path P from S to T. It means that we look at the residual. This is the matching, okay? So this is the residual, okay? So at first, right, the residual network like this, okay? Then we look at the residual network. We find whether any path from S to T or not. Okay, so we can see one path, right? For example, from S to J1 to W6, right? W6 to the T. Then what we do, we update the original matching network by adding this. So we just highlight this. So the red one is the one that we highlight. This is the flow we found. Okay, and then we update the residual network. How we update it? So we have the algorithm to update. Okay, so for example, first we have this one, right? So the original network and the residual network, they're identical because there's no flow at all. Okay, no flow at the beginning. We haven't find any flow. So they are, identical. Then this is the, the algorithm. Okay. So it takes the original graph G, okay, and the source and the sink, right? Source and the target one, okay. And at the beginning, right, because we don't have any flow, so we put on the flow EF, okay, and capacity EC, you remember, right? So we put on the flow E1. It means that we don't have any flow yet, okay. Then what we do, we look into the residual network. Residual network is denoted by the GF, okay. They are residual network, GF. G is original network, and GF is residual network. So we see whether any path from S to T or not. If there is, then we just, what we do, okay. So if there any path, right? So for example, for this one, we found one path, right? This is one path from in the residual network. It's one path, right? Then what we do? If we found a path, then what we do? We found this, right? Okay, we found this. Well, we found a path, and we choose the minimum flow in this path. But because for our methods, because of matching problem, right, on the flow equal 1, so the semi on way 1, okay. So we just find the in the path, right, what is the minimum capacity, okay. But because on the path, the capacity on way 1, right, yeah, equal 1, right, on way equal 1. So that's why the CME also 1, right? Mean up on the 1 value also 1, okay. Then what we do, we adding the new flow to the network, okay. So we adding the new flow to the network. So we just update the new flow to the network. And this is if the flow is in original network, then we update it, right? Then what we do, we update the residual graph, okay. But if the residual graph have the original one from U to V, then we minus it, okay. It means that because all the thing is 1, right? So we minus 1 will be 0. So we delete it. Then we add the new one. From original from U to V, we add a new one from V to U. So that is the flow from V to U will be original 1, 0, right? We add 1. Okay, because it means only 1, right? So it means that we just revert the flow. Okay. So for example, this one. Okay. So this is the original one, right? Then we found one flow in the residual network. Then what we do? We update it in original network. Okay, I found one flow. Okay, so we update, we highlight it in the red color. Okay, on the left hand side, right? You can see the flow. And then on the residual network, at the beginning, right, is from S to T. Now we reverse it from T to S. Okay, so we add sorry, what's wrong with my point? Okay. So reversely, if from S to T, now we have from T to S, right? We reverse this. So we, right? Then what we do? We also continue doing that, right? Because we do the for loop. If we do the while loop, right? Still, if we still can find a path from S to T in the residual network, then we continue. Okay. For example, this one. Okay. So this one, after we found this path, then we reverse, right? Now we do next. We see any path from S to T in the residual network. Yes, right. For example, from S to J2, J2 to W7, W7 to T. This is a new path. Then what we do? We update it into the original graph, right? So we update it into this graph. So we highlight it. You can see the red one, right? We found a new graph in the we found a new path in the residual graph. Then we record it in the network graph. So that's one. Yeah, you can see we highlight the red color. Okay, that's the flow we found. Then we also update the residual graph. You see the residual graph original here is a red color here, right? Now we update it by reversing. Okay, reverse it like this. And see, we reverse the direction. Okay, original this is sorry, yeah, original is like that. Then we reverse it. Okay. Yep. Then we continue, right? Now we're looking into the residual graph. There any additional one? You can see there is, right? From S to T. So there is, for example, S from to J3, 3 to W8, and W8 to T, right? So new one. So what we do? We update it in the original graph, right? So we highlight, you can see S to J3, S to J3, J3 to W8, and W8 to T, right? So we highlight it. Oh, sorry, W9. For example, we choose a W9. Okay. Instead of W8, we choose a W9. Okay. For example, we found this path. Okay. Then we update into the original graph. Okay. That's the original one. Okay. We update it. Then we update the residual graph, right? We reverse this. You can see we reverse it, right? Correct? I will let you know later. Okay. So which part of the course is reverse one, right? This one. This one is reverse one. CF of the FVU. So you just add it with the C mean. C mean only one, and this one original is 0, right? They know reverse one. Then we add it 1, so it becomes the reverse one. And the original one is 1, right? CFUV is 1 in the residual network. 1. You minus with 1, so it becomes 0. So that's the reverse one. Okay. So D2 is reverse one. Update the residual graph. Understand? Yeah, F is original graph, and the CF is the residual graph. Okay. F is original, and CF is the residual. Okay. So we have two graphs. One is original graph, yeah, F1. They are CF. Okay. Yeah. So after this one, we found this one, so we update it also. So easy to understand. Then any other additional one from S to T from the residual graph. From this one, any path from S to T. So you can see actually there is here. Go here, right? You look at the arrow. Go here, and go here, right? It's quite a complicated, right? But this is one path, right? From S to T in the residual one. Okay. We found this one. So they highlight the red color one. Okay. The new one. So what we do, we also update it into the, we update it, right, into the original graph. But how it works? Because you can see this one, right? You have the reverse one, you see? But this one in the original graph, we have this one only. From J3 to W9. Now from residual graph, you have the W9 to J3. So how you update it? Okay, so then, yeah, you look at this, right? So there is something mismatch. Okay. So how we do that? And also, for example, J3 to W8, J3 to W8. Okay, so how we do that? So you look at because when we do the updating, right, we had a checking. We check if the UV in the original graph, then we do that. But if not in the original graph, right? So that is the case. This one, W9 to the J3 is not in the original graph. Original graph, we have the J3 to W9, right? But now in the residual graph, in the path, we have the W9 to J3. So it means that it's not in the original one, right? If not in the original one, then we do the else. This is the else. So what the else mean? We remove a flow in the opposite direction in the original one. F is our original route. So we remove it by minus mean remove mean minus mean that we remove. We remove it in the original route. It means that original route. This is original one, right? From J3 to W9, right? Now we need to remove it. Okay. Let's see. So how we remove that? So maybe I delete this for you to easy observe. Okay. So I already highlight. So you look at this, right? If UV belong to E, if not belong to E, then we do the else, right? So this one, sorry, W9 to J3, not in the original graph, right? So what we do, we delete the flow, okay? So the flow from V to U will be deleted from the original graph, the F1, okay? So that's why we delete it. Okay, J3 to W9, okay? Right? So we delete it. So that's why we make it not highlight. W3 to J3 to W9 in the original graph. We delete it. So because original they are red color, right? We delete it, then we become the black one. Black one there is no flow, right? I mean delete means that we update the flow, not delete from the original graph, but we update the flow. F is the flow. So we remove the flow. Okay. Sorry, it means that we remove a flow. Okay. So originally we have the flow from J3 to W9, but we remove this flow. So the J3 to W9 is removed. Okay. So it becomes the black one. Yeah. Okay. Then we just update the new flow. The other new flow we just update, right? The other thing is just S to J5, J5 to W9, right? J3 to W8, W8 to T. So we keep the same. Okay, we just remove from J3 to W9. But J3 to W8 we keep it, right? So you see this one we keep S to J5, J5 to W9 we keep. But we remove the W9 to J3 because they are not in the original one. But we add the flow J3 to W8, W8 to T. So you can see the fourth thing we make it red. S to J5, J5 to W9. But W9 to J3, they are not in the flow. So we remove the flow here, but we still add the J3 to W8, W8 to T. Then we reverse it in the residual graph. So we reverse it. Okay, reverse the flow. Yeah, right. Originally is from S to T, now become T to S in this flow. Okay. And then, do we have any other flow from S to T in the residual route? S to T, any flow? No, right? Because the only thing is from S to G4, but G4 go nowhere. Okay. So we don't have any additional flow from S to T. So we stop, and that's done. Okay. So then after that, the final flow we can see is 4-1, the red one. First is from S, from this one, right? Second is this one. Third is this one. And the last is this one. So it means that the total number will be 4, right? Because at T we have 4 flow into it on red color. So the total will be 4. Yeah. So the answer for this question is 4. Okay. Yep. Okay. Any question about that? So that's the algorithm. Okay. So the algorithm means that every time, right, we keep track original route and the residual route. So at the beginning, there's no flow in the original route. So the original route and the residual route will be identical. And then we look at every time we look at the residual route, if there any flow from source to the sink, then we update it in the original route. Okay. But for every edge in the path, right? If that for every edge in the path, right? You see every edge in the path, right? If the edge happen in the original one, then okay, we add the flow in the original route. So we add the flow, right? Then we reverse the direction in the residual route. But if the edge not in the original route, right? If the X is not in original route, then we remove the flow in the original route. That's it. What problem we can solve in by using this algorithm, right? This algorithm can be solved, in many problems. For example, because it's a matching problem, right? So it can be solved by matching the CV. For example, you have you are recruiting the candidate for a few position. Okay, for a few position, you have a list of position. For example, you establish the company, so there are many positions, right? The accounting, the engineer, blah blah something, many positions, and you have a list of the CV. Then you need to match it so that you can have the maximum number of matching, right? So that's the one thing. The second thing is, as long as there's a matching problem, then you can solve it, right? For example, you have the network with, or you have the network, for example, the flight and the airport, right? You try to match it so that the maximum of the flow, maximum of the flight that can be used the airport or something, right? So they are more about the maximization of the matching. So you have two lists, you want to match it, then you can use it algorithm to use to apply. Okay, so that we can find the maximum matching. That is the problem. Okay, so in summary, right, we study about the 4 focusing methods, right? It uses a maximum flow problem, okay, and maximum matching problem. And normally, right, how you can find the path from S to T in the residual graph, right? Because normally every time we need to find from S to T any additional graph, any additional path, right? How we do that? You remember we did it using the breakfast search or the left search, right? Using a graph, okay? Then you can use a breakfast search or left search to find a path from S to T, right? Using the breakfast search or left search, right? We do it in the assignment 6, right? Yeah, so you can do the breadth first or depth first to find the path, or any rough troubleshoot methods. Okay, and a matching problem is just a 0-1 weight graph or the unweighted graph, right? But in the general flow network, the value can be the more than 1. Okay, but because of matching, we just 0 or 1 match or not. So that's why the weight of the graph is just 0 or 1. So it's easier to implement. Okay. Yeah, this is the in the computer vision or something, we also can use this. This is called a maximum flow, or they call it mean cut. For example, what the mean cut mean? It means that you had a network where you can cut it or not, so that you can break the network or something. It's like to find the weak edge, or you find the bottleneck in the network, right? So that if later you can, you can improve that so that you don't have any bottleneck in the network or something. Okay. Yeah, so there are a few applications. If you have time, you can look at this paper. Yeah, they mentioned about applying the energy, also applying the computer vision, yeah, to use the methods. Okay. So yeah, I think that's all for the matching problem. So any question about that? Okay, for the assignment 7 and 9, I will release by today or tomorrow. If the system has a problem, then maybe tomorrow. If the system okay, then I will release today. Okay. When do we decide to use a tree or graph? It depends. If just finding the path, then you can use the. It depends on the input, right? Input is a tree or input a graph, right? If the network, then normally the input is a graph, right? It depends on your problem. Yeah. But normally, if the problem is the network, then we use a graph. So what do you do if one edge doesn't get reversed? We need to update the reverse one. Yes. So I'm not so sure what you mean by if one edge doesn't get the reverse. So you mean at the reverse step or at the updating one? Updating, we always reverse the path in the residual graph. It means that when we found the path in the residual graph, then we just reverse this path in the residual graph. Okay. For the original graph, right? If they are not original, the edge is not the original one, then we need to remove the flow in the original one. Okay. In the step where you reverse the path from S to D, if the path are such that that doesn't get reversed. You can always, because you first need to find the path from S to T, right? From S to T. Then after that, you just do the reverse. So I don't catch what you mean by doesn't get reversed. Because you can always reverse, right? You reverse, just reverse the other. After the while finding a path from S to T. Okay, so I just back to this. Okay, I back to this. Okay. So Okay, we're back to original algorithm first, one by one. File a path, right? Then this one is just finding the minimum flow, minimum capacity. But because for our methods, right, if there's a flow, right, then we find the minimum capacity. But because for our methods, the capacity for on the edge on way one, so it return one. It's just a. But for the general solution of general network flow, right? For example, in the path you have like some edge have the capacity 3, 4, 6, 1 or something. Then you need to find the minimum one. So yeah, okay. Then another one you mentioned the flow. Okay, the path that didn't get reversed from J5 to W6. J5 to W6. Because they are did not the flow did not the path were interesting. We didn't use the path from J5 to W6, so we just put there. Yeah, we didn't touch it. So we only touch the path that we are interesting. For example, the path from for example this one S to T. Then we only reverse the path from S to T. Okay. So every time we find one available path, for example from S to J1 to W6, W6 to T, then we just reverse it. Okay. So the one that not in the interesting order, for example S, because they're from S to T at the beginning, there's so many paths, right? We just choose one. You choose this one, then you reverse it. If you choose this one, then you reverse it. Yeah, that's it. If we don't choose, then we don't reverse. If there are flow in residual graph, and if yes, correct. This one will use a breadth search or depth search to find the path. Okay. Then every time we just find one path. We just select one path. If the flow in the residual graph, and if you be we just add one. Because for our methods, the capacity is one, so it's just one. If we use this flow, then we cannot reuse one more time. Yeah. Okay. So for example, if we use this flow, right? Then of course later we cannot use this flow because the capacity here only one, right? So either go here, right? Either go J2, right? Either you just go W6 or W7. You cannot go both W6 and W7 because here the capacity one, it means that capacity here must be 2, right? If you go both, right? Okay. So any other question? So remember the assignment 6 deadline is tonight, so you need to submit it. Okay. Next week there will be just a review lecture. So there's still the lecture, but just a review, and I will maybe try to answer some question in the assignment or something. Yeah, if you have any. So if more next week is no new lecture. It's just about the review lecture and some question and answering. Okay. No, for this assignment, the new assignment 7 and 8, you cannot ask. You can only ask the assignment 5 and 6. No, assignment 7 and 8 still 3 questions. So still only 3 questions for the remaining one, and 5 the MCQ. So it's just like the assignment 5 and 6. It's not about the combining. I combine. I mean, I increase the number of questions. It's not about that. You still have 3 questions to solve. Okay. Oh, sorry. Assignment 6. Deadline tomorrow. Yeah. Sorry. Yeah. Tomorrow night. Not tonight. Yeah. Not tonight. Tomorrow night. Yes. The assignment 6 will be 10% because I combine assignment 7 and 8. Okay. Yeah, still have the 5 MCQ question. 5 MCQ question and 3 programming questions. I will release tonight or tomorrow, I'm thinking. Yeah. But the deadline is still 2 weeks after I release. So no worry about the whether you have time or not. Yeah. Still have still 2 weeks. The rate, I'm not so sure. I need to check with the school whether I can release the rate of the assignment or not. I heard that I cannot, but I need to double check with the school. Yeah. Because I heard that the I can. Oh really? The first half release? I mean release after the assignment or after the first half? Oh, that's why I need to double check. Okay, if I can release, I will release. But in next week, I also answer the question there. Okay, give you some solution there, something that you can know that okay whether you do correct or not. I heard about that he released the first and second. Okay. Okay, yeah. Okay, let me check and whether I can release or not. Okay, if I can, then I will release. No worry. He released the rate or he released the score? Because the rate need to be calculated at the end of the semester. Yeah, should be the score, right? Not the rate. Okay. Yeah, if I can release the score, I will release. Okay. But he released the whole file. Then or he just sent the individual email. At NTU Learn. Okay, let me check. Double check. Okay, I see. But then everyone can see the score of the others. Really? No. Okay. Okay, I see. Okay, let me ask him how to do that. Because 700 students, and how can there should be a way to do that. Okay. Okay, any other question? Let me stop the recording.